So yesterday, since I messed up the explanation really bad for the proof of axis of symmetry, and I didn't explain quadratic inequalities, I'm gonna explain that today. So basically, as a reminder, the general form is in the form of ax squared plus bx plus c. And apparently, to find the axis of symmetry, you can use the formula of b minus b over 2a. And the reason for this, because this formula, if you turn it into completing the square, there's some relationships that you can see which helps you derive this particular formula. So if you wanna, if you have this as your quadratic equation and you want to complete the square, so to complete the square, you have to factor out the a. And how you do it is that you divide everything by a, so the a can go out. And then after that, you try to complete the square, like what we did yesterday. B over ax, and then plus the squared amount plus c over a minus the squared amount close to 0. Close to 0. So to find this, you would have to divide b over a by 2 and then square it for the value here. So that would be b over 2a squared plus c over a minus b over 2a squared to make sure that the equation is balanced. So b over 2a. So from this, you can finally factor out this into somewhat this form and complete the square. So it becomes x plus b over 2a, a plus c over a minus b squared over 4a squared. So if you compare this formula, it is also, you can say that it is comparable to this particular formula, x minus h squared plus k. So we can pretty much say that like minus h is the equivalent of b over 2a. And k is the equivalent of c over a minus b squared over 4a squared. And from this, h would be b over 2a minus b over 2a. And as you can see, the property in this particular formula is that the axis of symmetry is equals to h. So since h is equals to minus b over 2a, that means that we can just immediately use this formula when you have ax squared plus bx plus c, and by inserting minus b over 2a from this particular formula, you can easily get the axis of symmetry. Then next up, we have quadratic inequalities. So quadratic inequalities, in essence, is kind of pretty much similar to finding ax squared plus bx plus c. it's similar to finding this, but the difference is that the sign here is less than or more than. So the differences between it is that, for example, if you find two values of x, let's say x has the value of p and q, then these values would need to be assigned with the more or less sign, depending on what it's asking. So to easily understand this, let's just think about it in a more visual way. Let's just say we have the graph of ax squared plus bx plus c. The graph would look something like this. And then this would be point Q. This would be point P, and this would be point Q. And so whatever it's asking, in the case of the function ax squared plus bx plus c, it should be less than 0. Then it's asking, what it's essentially asking is asking for the negative values. And the negative values in this case would be this particular area, which is the between P and Q. So if you want to write it, it would be something like this: P, X, Q. Well, this part is where the values are positive. So if they ask for something like ax squared plus bx plus c, we're in 0. That means that this is negative values, and then this is positive values. So this is essentially asking for you which values are bigger than 0, or which values are positive. And therefore, if we have these as its roots, then we can say that x smaller than p, comma, x bigger than q. And if you want to mathematically write this, like in notation form, then that would be something like infinity, comma, q. Oh wait, sorry, my bad. This is supposed to be p. P, and then n, q, comma, infinity. Or if you want to write it in, there are several ways for you to write it. There's also the set notation format. We write it in form of x, p, x, and q. So yeah, there are several ways to write it. Okay, so since I've covered this, I think. Oh wait, and okay. So another thing. So sometimes when you have ax squared plus bx plus c, for example, we're in 0, you don't know. You're most likely going to have a formula, and you're not going to have a graph in front of you. So to find the roots, before actually like look for the roots, you can always figure out how the graph approximately looks like by plugging into the discriminant. So this will help you a lot, because by plugging into the discriminant, it helps you figure out if the formula or the equation has 1 root, 2 roots, or no roots. So you don't have So you don't have to bothersomely plug in A, B, and C into the quadratic equation, especially if the numbers are really whack. And by finding it, you can figure out like an estimate of, oh, maybe it would only have one solution. So maybe it's easier to factorize it. But then maybe if it has two roots, you can factorize it or input in the solution. And then if you find that there's no solution, then you don't need to bothersomely plug it into the equation and find out that there's non-real roots. So yeah, there's that. Okay. And then next up, we're finally going into chapter 15. Okay. So in chapter 15, we're focusing on functions. Before we learn functions, we need to know some basic terms relating to function. And the first one would be about relation. So relation is any set of points in the xy plane. So for example, if we have an xy plane, and then we have, let's say we have this line, then that would be a relation. Or if you have this shape, that would also be a relation. Or even if you have something like this, where x is more than 0 and y is more than 0. So like this area of set of points, that would also be considered a relation. Or if you have a set of dots together, that would also be what you call as a relation. So from you can see before, there are like a lot of relations, but the general gist that we want to know is that whether the relation have an equation or whether it doesn't have an equation. And in the case of, like I said before, the several dots, then there will be no equation, because how can you compute dots into like a certain shape or form? Or for the one with the area before, that is also not an equation, because it's not like a line going through some places. Examples of equations would be the straight line, the parabola, the I don't know what this is called, but whatever this is called, and maybe like the unit circle, and etc. etc. Basically any kind in general which has an actual equation. Because like if you draw something like this, wait, actually, like this, then the equation here would be x equals to y squared. And if you draw something like this, then the equation would be ax to the power of 3 plus bx plus c. So you can like establish a relationship between the y and the x. And for equations, we also have a special equation, which is called function. So function is a special, well, is one of the special relations because it only has one x coordinate output. So for example, if you have something like this is a function. Or if you have something like this is also a function. If you have something like whatever weird shapes like this, maybe this is also a function. So anything can be a function as long as you only have one x input. So what I mean by like one x input is basically like the x input doesn't double. Like in the case of this, in this form, this is not what you call a function because there are two x values at the same time. You can only have one x value at once when you have a function. And then another thing that you can obviously see because of this requirement is that if you, let's just say we have this kind of thing, kind of shape. If you draw vertical lines along the graph, and the vertical lines only intersect once with the graph, that means that that would be considered a function. So if you have something like this, yeah, let's just say we have the unit circle, then this would not be a function, because if you draw vertical lines, you can see that some when we draw vertical lines, you have 2 points that intersect the graph, and that's not how functions are supposed to work. Okay, so after that, we also have some graph notations that you should know. So by the way, this is what you call as a piecewise function. So a piecewise function is a function that has kind of like two pieces, you know, piecewise. So as long as the function has two equations, like this one, you have three equations to define the function. This is what you would call as a piecewise function. So in the case of a piecewise function, if you have a circle, that means that the value is not included. For example, let's just say this is 1, this is -1. And in the case of this, let's just say this is colored, this is only a circle. So this value would be not included. Or in other words, this line would be like the x values would be written as -1. Let's just circle this here. -1 x smaller than 1. So the 1 is not a part of this equation, but part of this equation. And then, for example, if you have the sign, the arrow sign, it means that it continues indefinitely. So it goes from 1 to, yeah, it goes from 1 to infinity. Okay, and then after that, there's okay, so there's the function notation. So in math, we have several function notations, which is the fx or the f dot. I don't know what this is called, but it looks like something like this, and something like this. So basically, what this is trying to depict when you have it in front of your equation, like let's just say something like this. What this is trying to say is basically we can imagine something like a machine going in. Let's just say this is the input. So the input is x. And then after inputting it x, then it goes into a process where something happens depending on the equation. So you have input and then you have output. Okay, so since this is not very clear, let's just have the example of this function as 2x plus 5. So what happens is that if you insert x in, then the result you get that comes out of it would be 2x plus 5. So in this inside this machine is what happens when you pretty much use the 2x plus 5. So basically if you have let's just say we insert x as 1. So we input 1 and x gets replaced as 1. So that would be 2 times 1 plus 5. 2 times 1 plus 5 would mean that your output would be 7. So you can see that basically what this is saying is just from input of machine to output of machine, something like that. Okay. And then after that we have this thing called domain and range. So if you want to input something into the machine, you cannot always input whatever you want. In some circumstances, there is a limit to how much you can to how much you can input, and that's what you call as the domain. So if drawn in a graph, for example, we have the function of 2x plus 5, so something like this. The domain of this graph would be the values of x-axis. And then the range of it, domain, the range of it would be the values of y-axis. And when I say the values of x-axis or the values of y-axis, I refer to any of the values that they can do. So in the case of this equation, it might be that the values would be infinite since it's just a straight line. But there are also in some other cases where in other functions the values are limited. For example, if the fx is equals to x squared. So perhaps the domain might have unlimited values, but then the range of it, the y-axis, only has limited value, which is 0 or more than 0. So you can write it this way. And basically, these two, domain and range, they are usually written in the set notations, the bracket notations, or the number line graph. The set notations, if we recall, which I've actually covered, would be something like this. And then for the bracket notations, it would be something like this. For the number line graph, it would be something like this. Actually, if there's no equal sign, it would have looked like this. This version is if it's this. So for the number line graph, it would look like something like A, B, values. Okay, so how do you find domain or range? I don't think there's a concrete way or explanation on how to find domain or range of everything, but there's not a specific guide on how to do it because there's too much functions out there. Maybe even if they teach you how to do it, they only teach you the common graphs. So honestly, the best advice for this is to know the properties of the functions that you've learned regarding graphs. Like how if it's quadratics, then it's in the form of u's, and how in the form of x3, it's in the form of like waves, like one wave, and then how reciprocals would have like their own function, will have their own unique function or shape, for example, like this, and etc. etc. So basically, like, know your properties and apply it in the situation. So now we're going into rational functions. In this case, we're going into reciprocals specifically. Okay, so before we go into that, there are some definitions that you need to know. The first one would be polynomials. So polynomials are basically the functions or the equations where you have x to the power. Basically, like any equation with x and a power, whatever the power is what you call polynomial functions. And we also have this term called rational functions, where the function is a polynomial function which is divided by another polynomial. And one of them is reciprocal functions. So reciprocal functions are written in the form of y equals to k over x. And how it looks like in a graph usually would be something like this. So this shape is what you call as a rectangular hyperbola. And I don't know why it's named like that, but yes, that's its name. Okay, so take the example of to explore this function, let's just take the example of y equals to 1 over x. So if you have a graph like this, this is the drawing of the graph, then we can establish that one of the properties would be the domain of this graph is any value as long as x is not equal to 0. Because the value of 0, as seen on this graph, is basically infinity. So, or if not infinity, it would be undefined. Therefore, any value that you want to insert in this graph is all right as long as it's not 0. And then the second property that you can observe from this would be that they have two asymptotes. So, okay, so brief review to what asymptotes mean. Asymptom is the particular asymptom is essentially like that one value that the graph is approaching but not touching. So if you have something like this, is commonly found in graphs like exponentials or graphs like logistic functions. Typically, you will always have that one value that the equation is touching, but they're not equal to that value. It's like it's approaching it, but it's not equal to it. But it's very, very close to equal to it, but it's just not quite. Like in the case of logistic functions, usually they will always have one horizontal asymptote. And yeah, like I said before, the graph is always approaching that one value but not touching it. And in this case, they have the reciprocal function have the horizontal asymptote, and the vertical asymptote. The vertical asymptote would be this particular asymptote where x is trying to approach 0, but not quite approaching 0. And for the horizontal asymptote, it's where y is it's where the y value is trying to approach 0, but it's not quite approaching 0 yet. So if you want to write this down, it would be that x tends to 0 plus from the right, and when x tends to 0 from the right, x tends to infinity. And when x tends to 0 from the left, x pretty much tends to like minus infinity, and so on and so on. Okay. So next we have composite functions. Composite functions is what happens when you have usually two or more functions together. And we can take the example of fx and gx. So let's just say that fx is equal to x plus 3, and then gx is equal to 2 to the power of x. And let's just imagine this as like in form of machine. So if we have f parentheses gx parentheses, then this is kind of like saying that so after you put in this value, you insert it into the x. So like after you insert an output from G, no, after you insert an input from G, you get the output of G. And you insert the output of G into the input of X. So if you want to draw it visually, it would become something like this. So we input X, and then 2x. This is G. So the output that goes out is 2x to the power 2 to the power of x. And then you insert it into x plus 3, which would be 2x plus 3. And that's the output that you get. This is the equivalent of writing something like FOG x or FOG x. So this and these are the same. Oh, and an important thing to keep in mind is that when fx gx, this is not equal to g fx. Because if you see from this machine below, if you think about it, that's like this is essentially saying that we have input x, and then we get the output of x, the output of fx, and after getting the output of fx, we insert it into gx. So if we have g fx, that would be the equivalent of 2 to the power of x plus 3. And then after that, we have inverse functions. Inverse functions is what happens when you want to undo the process of the machine that we have just now. But not all machines can be undone. There are only certain machines that can be undone. So examples, okay, so again, this depends on the function, the type of function that you have. If you have, so basically we have several types of functions. The first one would be the one-to-one function, where in every x value, there is only one y value. There will always be one y value. This is what you call the one-to-one function. And then we also have another function in which we call as many-to-one. These functions would be the type that's usually quadratics, polynomials. This is when in every 1x value, there can be more than one y. So there can be like one value of y, there can be two values of y, or in some cases there might even be three values of y.
You mean more value?
Yeah, more values
of x for the same y.
More values of x that has the same y.
Yeah.
Yeah, my bad. So the only kind of function that can be reversible would be the one-to-one function, because if you have x values, like if you have some x values which has the same y value, then how are you going to reverse it? Am I right? Mm-hmm. Okay, so a way to identify the one-to-many function would be to do the horizontal and the vertical test. If it fails the horizontal test, basically the horizontal test is similar to the vertical test, where like you draw horizontal lines and see how many intersections they have in the graph. If they have two intersections or more than two intersections, that means that it's definitely a one-to-many function. But if they only have one intersection, then it's definitely a one-to-one function. So an easy way to inverse the function is literally just, okay, let's just say we have a function that is fx equals to 2x plus 3. To reverse it, you literally just exchange, let's just assume that fx is equals to y. So y equals to 2x plus 3, and then you replace the x and the y. and like literally flip their variables, so it becomes x equals to 2y plus 3. And after that, you make y the subject. So x minus 2 over 3. Wait, no, x minus 3 over 2 is equal to y. That's how you find the inverse of the function. Okay, so something that you can like know, or something that you should at least keep in mind when you look for the inverse of the function is basically that an inverse of a function is essentially a mirror of the function in x equals to y. So if you have if you have a line like this, an equation like this, then the reflection of the equation, which would be maybe like something like this-ish. Let me, yeah, something like this-ish would be the inverse of it. Or if I, yeah, I think it is something like this-ish. So since it's in the reflection of y equals x, there are also some cases when functions do not have the same formula as their inverse. And this is seen by some functions that are self-inverse, such as the reciprocal formula y equals to 1 over x, because the shape is something like this. Or I can't remember anything else, but like one of them is something like that. Oh, and something else you can know is basically if you have y equals x, that's basically like the identity function, or like the source of the mirror. It's called identity function, and I don't know why it's called that for a reason. And so since they are like y equals x reflections of each other, then we can say that the inverse of x times the function of x is equal to x. So that should be pretty much it for today's session.